As a wise person once said, ogres, in Recursion, are like onions. They have layers. Hi, Rodolph here again. I'm sure you're all eager to bounce back into Recursion, or at least understand why I'm referencing this quote from Shrek. Join me as we cut into this statement to see how onions could help us cook up our own recursive functions in this episode of Algomations. First off, I'm assuming y'all have a basic understanding of recursion from the last episode here, so if you haven't watched it yet, feel free to pause, watch it, and come back here once you're done. With that being said, let's cook up our first recursive function. One way we can use recursion is to calculate numbers like factorials and Fibonacci numbers. We'll start with the former. The factorial of a number n is generally defined as the product of all numbers from 1 to n, with the exception of 0, whose factorial is defined as just 1. It follows then that 1 factorial is 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1 times 2 times 3, which is 6, and so on for every number that comes after. We could view the factorial as an onion slice made up of layers of onion rings and an onion core. Each ring and the core represent a number to be multiplied in factorial, while the slice represents the final factorial product. So the 3 factorial onion slice would be composed of 2 multiplier rings times 2 and times 3, and a core valued at 1, whose collective product value is 6. We could also view this onion slice as being made up of smaller, concentric onion slices. Referring back to our factorial equations, we see that 1 times 2 is equal to 2 factorial. So our 2 factorial slice would be a 2 times multiplier ring surrounding the 1 valued core. With this, we could also say that our 3 factorial slice is a 3 times multiplier ring surrounding a 2 factorial slice. Furthermore, since 1 is 1 factorial, we could even say that the 2 factorial slice is a 2 times multiplier ring surrounding a 1 factorial onion slice, even if the onion slice is just an onion core. Likewise, we can see that this onion slice representation emerges as a pattern with our numerical equations, where 3 factorial is 2 factorial times 3, and 2 factorial is 1 factorial times 2. It turns out that this pattern follows for all factorials thereafter, which gives us the recursive formula n factorial is equal to n minus 1 factorial times n. Now let's say that we wanted to write up a program that can calculate the factorial. We could use a for loop to calculate the factorial, which would be like building an onion slice layer by layer, from the core to the outermost layer. Referring to our recursive formula, however, we could also calculate the factorial by using a recursive function, in which we assemble the onion slice starting with the outermost layer and working our way inwards towards the core, then building up all the slices until we get our final slice. But how do we make such a function? How do we build our own onion slices outside in? Well, we want to be able to build an onion slice of any size, down to the smallest slices, or our onion cores with no layers. Thus, for any recursive function, we'll set up 2 cases, the core, or the base case, and the layer, or the recursive case. Since all of our onion slices have to have a core, let's start with the base case. We could have our core represent 1 factorial, as it has the smallest value. However, we could also make our core be 0 factorial, as 0 is the smallest number that has a factorial associated with it. 0 factorial is also valued at 1, so let's use 0 as our core/base case. So if our input n is equal to 0, then we'll return 0 factorial, which is just 1. Now, we move to the layer, or the recursive case, which will cover all values greater than our smallest value of 0. Here, we want to define how our outermost layers should interact with the smaller recursive onion slices they surround. We recall the recursive formula that we got from before, which essentially says that a factorial onion slice is a multiplier ring times n that surrounds and multiplies the value of the onion slice that is the factorial of the number before n minus 1. In our recursive case, the behavior of the outermost layer is represented by the times n operation, while the smaller onion slice that it acts on is represented by the recursive function call to fact n minus 1. Now let's do a run through to see that our factorial function works out. Let's try computing 3 factorial. Since 3 is greater than 0, we'll go to the recursive else case, where we multiply the result of fact2 with 3. Similarly, in the fact2 call, since 2 is greater than 0, we multiply the result of the fact1 call with 2. Within the fact1 call, we multiply the result of fact0 with 1. Finally, in the fact0 call, since 0 is equal to 0, we just return 1. Now that we have the result of fact0, it can be multiplied with 1 to get back fact1, which is 1. Fact1 then can be multiplied with 2 to get back fact2, which is 2. Finally, fact 2 can be multiplied with 3 to give back fact 3, which is 6. Yay, we successfully built up our factorial onion slice and got the correct value. Now, in the case of the factorial or other similar operations such as summing all the numbers from 1 to n, it is far easier, if not more beneficial, to use the for loop. So why use recursion? For our factorials, we know what we should be getting for any call to fact n, which is the product of all numbers from 1 to n, i.e., we can clearly see all the smaller onion slices that make up the big onion slice. However, there are cases where we might not immediately know what all the smaller onion slices look like in a given onion slice. Take Fibonacci numbers, for example. Fibonacci numbers are numbers in a Fibonacci sequence, with the nth Fibonacci number f sub n being defined with the following formula, where f sub n minus 1 is the Fibonacci number before f sub n, and f sub n minus 2 is the Fibonacci number before f sub n minus 1. For example, the fourth Fibonacci number would be the third Fibonacci number 2 added to the second Fibonacci number 1, which is 3. However, without knowing all the Fibonacci numbers in advance, it would be difficult to determine the nth Fibonacci number in the sequence just by looking at the formula, especially for larger values of n. If each term from the Fibonacci formula were represented as onion slices, we can clearly identify the two onion slices, f sub n minus 1 and f sub n minus 2, and the outermost layer, the addition operation that surrounds them. But it's hard to immediately make out the inner slices that compose f sub n minus 1 and f sub n minus 2. Here, recursion definitely trumps the loop, because we don't need to know every Fibonacci number beforehand. We only need to know the first two terms, f sub 0 and f sub 1, which are 0 and 1 respectively. Given these two onion cores, and the aforementioned Fibonacci onion structure, try taking a jab at generating the corresponding program to calculate the Fibonacci numbers. While I won't give the answer directly in this video, the answer will be posted down below in the comments. And with that, hopefully y'all can start making your own recursive functions to carry out some cool calculations, or count bananas, your call. Next time, we'll start diving into some recursive algorithms that'll put the alg in Algomations. Anyways, I've cooked up some onion rings, so come and get some.